Hello everyone! In this lecture, we are going to discuss the second type of electric machines, and these are the electric generators. So let me take you through what we will be going to discuss during the lecture. So in today's lecture, we are going to discuss the electric generators. Generators are useful appliances that supply electrical power during a power outage and prevent discontinuity of daily activities or disruption of business operations. They are available in different electrical and physical configurations for use in different applications. In this lecture, we are going to look at some types of the generators. The basic one is the permanent magnet generator. We are going to discuss its basic principle of operation and the generator connection to electrical system. We are going to talk about some application examples as well as discuss the large PM generators. We will also discuss into details another type of generators called the wound field synchronous generators. We are going to come up with their equivalent circuit and we will discuss and analyze their phase diagram. So earlier we have discussed electrical motors that convert electrical energy into mechanical or rotational energy. On the contrary, generators, they are devices that convert motive power or mechanical energy into electrical power for use in an external circuit. And sources of this mechanical energy could include water, gas, steam, wind, or an aircraft engine. The generators provide electricity for transmission and distribution over power lines to domestic, commercial, and industrial customers. They also produce the electrical power required for automobiles, aircraft, ships, and trains. The reverse conversion of electrical energy into mechanical energy is done by the electric motor, as we discussed earlier, and that's why the motors and the generators, they share a lot of similarities. However, a generator does not actually create electrical energy. Instead, it uses the mechanical energy supplied to it to force the movement of electrical charges present in the wire of its winding through an external circuit. So this flow of electric charges constitutes the output electric current supplied by the generator. This mechanism can be understood by considering the generator to be analogous to a water pump, which causes the flow of water, but does not actually create the water flowing through it. So there are two types or two main categories of generators. The first one is the asynchronous generator, and the second one that we will discuss later is the synchronous generator. Modern-day generator works on the principle of electromagnetic induction, which was discovered by Michael Faraday in 1831. Faraday discovered that the flow of electric charges could be induced by moving an electric conductor, such as a wire that contains electric charges in a magnetic field. So this movement creates a voltage difference between the two ends of the wire or electrical conductor, which in turn causes the electric charges to flow, and this generates the electric current. Induction generators are asynchronous generator, which is a type of AC electrical generators that uses the principle of induction motors, which we discussed earlier before. Induction generators operate by mechanically turning their rotors faster than the synchronous speeds. That's why we can see that the induction generator operates in this region over here, which is beyond the synchronous speed. And in this case, for example, if we are talking about a wind turbine-based generator, it uses something called an induction machine double-fed induction generator. And this induction machine drives the wind drives the induction machine above the synchronous speed, which results in the sign of the torque to change from here to there, and this causes the electrical generation. So, in the context of wind turbines, the mechanical energy is obtained by capturing the energy in the wind with a turbine rotor, and in some turbines, converting that high torque and low speed into low torque and higher speed using a gearbox over here. Doubly fed electrical generators run at speeds slightly above or below their natural synchronous speed, mostly above. This is actually useful for large variable speed wind turbines because the wind speed can change suddenly. So double fed induction generator is based on an induction generator with its stator windings connected to the power grid, and the rotor winding connected to an AC to DC and to DC, DC to AC converter. So as you can see, the stator is connected to a power grid, and then the rotor is connected to a control system or a converter. And in this case, the converter converts the voltage source and controls the rotor and the grid currents. So in this case, the rotor frequency can freely differ from the grid frequency, and by using this converter to control the rotor currents, it is possible to adjust the active and reactive powers fed to the grid from the stator, even if the wind speed changes. In fact, there are three ways to move the rotor to produce a rotating magnetic field. By induction, as in the previous example where the used generator was asynchronous, or by permanent magnet, as we will discuss now in something called synchronous generators, or by using an external exciter, which is a small source of DC current that energizes the rotor, as we will discuss later on. So let's take a look here at the permanent magnet synchronous generator. This type of generator, in this type of generator, the excitation field is provided by a permanent magnet instead of a coil. So this is the permanent magnet over here in the middle. And in this case, the rotor structure can consist of a ring of magnetic iron with magnets mounted on its surface. And the term synchronous refers here to the fact that the rotor and the magnetic field induced in the stator rotate with the same speed because the magnetic field is generated through a shaft-mounted permanent magnet mechanism, and current is induced into the stationary stator. In this type, the center of the generator lies the rotor, which contains the magnet, and the stator is the stationary armature that is electrically connected to a load. So over here, this stator is connected to a load. These machines are superior alternatives to traditional induction motors that can be coupled with turbines, diesel generators, and used for hybrid vehicles. Another major advantage is that these machines do not require any specific work environment and hence can be used in wind and water machines. So imagine here with me that the wind causes the rotor to rotate, but remember the rotor has a permanent magnet mounted on it. So as the rotor is turning, the magnetic field produced by this permanent magnet is rotating as well. And the rotating magnetic field induces voltage into the stator. And once that is induced, an induced current starts flowing into the connections of the stator, and that's why the stator can be connected to any source of load or to any type of load. And because the permanent magnet is rotating as the rotor is moving, we can see that over one complete revolution, so let's say that the rotor turns from position A to B to C to D, accordingly, the magnetic flux will change the phase. So we can see here one full cycle so this is one revolution of the wind turbine and one full cycle of the change of the flux direction. It is important to note here that the voltage which is measured across the stator terminals or the stator windings is called the voltage, the per phase voltage. So if we are talking a single phase, this is the phase voltage which is connected to the load, and it is related to the number of turns on the stator windings. Also, it is important to note that the flux magnitude is fixed by the permanent magnet, And if we can see over here, the change in the flux is related to N, the number of turns. So the voltage that is produced across the stator is affected by the number of the turns as well as the change, the rate of the change of the flux over time. In fact, the relationship between the phase voltage and the turbine speed can be considered as a linear relationship. So as the speed increases, the phase voltage increases with it in a linear manner. So let's say that the speed is 30 RPM. In this case, the phase voltage can be measured as 1 volt. However, if the speed was doubled to 60 RPM, in this case, the phase voltage will also double. So if the flux that is generated by the permanent magnet is fixed, a good question is, how can we increase the PM generator output voltage? So in normal cases, we want a generator to operate as high a voltage as possible because this will limit the losses for a given power output. So remember that the voltage is dependent on the number of turns and the rate of change of the flux compared to time. So there are two options to increase the voltage. The first option is to increase the number of turns on the stator winding, and this would be limited by the I square R losses. The other thing is what we can do is to increase the rate of change of the flux. But we cannot change the flux magnitude itself, but we can change the rate of its change. So that's why the PM generators typically have a high number of magnet poles on the rotor, because this will result in a higher rate of change in the magnetic flux. So we can say that the generator output voltage frequency, it is a function of the speed of the generator, which we denote as NR, and the number of poles. And this would, any change of these would cause a change in the rate of the magnetic field, the change of the magnetic field, and that would lead to a change in the phase voltage. So given that the electrical frequency is the same frequency as the rotor, we call this type of machine a synchronous machine. And when I say electrical frequency, I mean the change of the output voltage. So that's why we can see that both the output voltage and the frequency or the speed of the generator are linearly proportional. Now the question is how to interface this to an electrical system. In order to answer this question, we need to understand what is the type of system or the type of load we are connecting this generator to. And in this case, there are two options. The first option is the connection to a standalone DC system. These typical applications are isolated locations and they require an electrical supply. This includes remote farmhouses, telecom station, mountain huts, small boats, a bulb, a fan, so any type of DC load. So what would happen in this case? That the stator is going to produce a variable voltage and a variable frequency AC output. But this is because the wind changes the speed. In order to change the variable AC to variable DC, we will need a diode rectifier component. And in order to change the variable DC into a fixed DC that is suitable to DC loads, we will need a power electronic DC to DC converter. On the other hand, if we are connecting the generator to an existing AC grid system, what we need first is, again, the diode rectifier to change the variable AC into a variable DC. And the voltage, because it's important to keep in mind that the voltage generated by a variable speed wind turbine is non-grid compliant. So to supply the transmission network with power from these turbines, the signal must be passed through a power inverter, which ensures that the frequency of the voltage of the electricity being generated by the wind turbine is the frequency of the transmission system when it is transferred onto the transmission system. So the role of this power inverter is to convert the signal to DC and then convert the DC signal to an AC signal, which is suitable to be connected to a grid connection or other types of AC loads. However, it is always desirable to have a three-phase machine because it is superior to its single-phase equivalent. So in order to have a three-phase permanent magnet generator, what could be done is to install a three-phase winding on the stator. So this is the stator over here. The three windings are separated physically from each other by 120 degrees. And that's why they produce a three-phase output voltage. And the voltage, the three voltages, they are separated by each other by 120 degrees, and they vary just as previously discussed over time. Three-phase PM generators could vary between small to big generators, and they are currently employed in many locations, as well as they have many uses. So for example, over here we can see this is a 6 kW proven generator on the island of Eigg in Scotland. This generator is by a company called Rutland. It produces 50 watt and that is for the purpose of boat charging. Also, another generator is by the company called Quiet Revolution, which produces 3.3 kilowatt of power, and this is a vertical axis turbine to supply power to a house or a company. Another type of small PM generator is the 2.5 kilowatt proven generator on the Shell gas rig. This is in the middle of the sea, and this type of generator is supplying power to the gas rig. But also, permanent magnets, they could be really big. The company called Enercon have been deploying permanent magnet wind turbines for a number of years, and their biggest generator is 10 megawatts. Can you imagine? Yes, 10 megawatts. All right, so how big this could go? There are some installations that require big generators, and one of them is the Longannet coal-powered electrical power station on the Firth of Forth in Scotland. It has two 300 megawatt electrical generators. This station is the third largest power station in Europe and the location for the UK's first carbon capture plant attached to a working coal-fired power station. The Krashan hydroelectrical scheme also uses four 100 megawatt electrical generators. Krashan is the world's first high-level reversible pumped storage scheme for generating hydroelectricity, and the power station is located deep inside a mountain. I'm going to stop over here, and in the next video we are going to discuss another type of synchronous generators, which are called the wound field synchronous generators.